This is our third lecture video for electrochemistry, and we're going to start this video series by looking at different types of batteries. And the first one that we're going to be looking at is an acidic dry cell, and this is a very basic type of battery. And we want to show you the different types of batteries just so that you realize that electrochemistry is part of your everyday life, especially now with so many electronics and phones and things that require batteries to help fuel our economy and the way that we live our life now with so many electronics. Now, here's a picture of a dry cell battery, and you've got the positive terminal, and you've got a graphite rod, which is the cathode, and then you have a moist paste of manganese oxide and ammonium chloride. And then the anode is going to be this zinc casing around it. So you've got a zinc casing around it, and that's going to act as the anode. And at the bottom here is the negative terminal. So the electrolyte in paste form is the zinc chloride and ammonium chloride, or you may have magnesium bromide. So the anode is zinc, and in some cases it may be magnesium, and the cathode is the graphite rod. So the reduction occurs at the cathode, and the manganese dioxide is reduced. So it goes from this manganese dioxide to this other manganese species. And this produces a voltage of 1.5 volts for this battery cell when you combine the oxidation half reaction and the reduction half reaction. Now most of these batteries, they're expensive, they're not rechargeable, they're also very heavy, and they're easily corroded. So these are some of the problems with these basic acidic dry cell batteries. Now an alkaline dry cell battery improves upon this a little bit. So it's the same basic cell as an acidic dry cell, except that the electrolyte is the alkaline potassium hydroxide paste. So again, the anode is the zinc, and you've got a brass rod, which is your cathode, and you've still got the reduction of the manganese dioxide. And so the cell voltage is about the same, so 1.54 volts. Now these alkaline dry cell batteries, so alkaline just meaning basic, has a longer shelf life than acidic dry cells, and they're rechargeable, and you have little corrosion of the zinc. So those are some of the advantages of some of the dry cell. Now lead storage batteries, so these are like the batteries in your cars. They actually have 6 cells in series, and a lot of times the electrolyte there is 30% sulfuric acid, and the anode is lead. So the lead sulfate, so the lead gets oxidized from lead 0 to lead 2 plus. And the cathode is lead coated with lead oxide, and the lead oxide is reduced to make the lead sulfate. And this produces a cell voltage of 2.09 volts. Now these are rechargeable like your car batteries are, but they're also very heavy. So if you've ever had to pick up a car battery, you know that they're very heavy. Now, since we're looking at the components of car batteries, I want to take this moment to just point out why it's important to properly dispose of any car batteries. Because lead is bad for the environment. Lead is a neurotoxin, and if it gets out into the environment, it leaches in the soil, it can contaminate the soil, and you have other various problems associated with it. But also, too, it's got a lot of sulfuric acid into it, and that sulfuric acid is very corrosive and can burn your skin. So you have to be very careful and dispose of car batteries very carefully and properly. Now another type of battery is the nickel-cadmium battery, and the electrolyte is concentrated potassium hydroxide. Here the anode is cadmium, and the cathode is nickel coated with nickel oxide. And it's the nickel oxide that gets reduced at the cathode. And that produces a cell voltage of about 1.3 volts. Now these nickel cadmiums are rechargeable. They have a very long life. They're light, so compared to the other batteries that look like they were very heavy, these are much lighter. But if you incorrectly recharge these batteries, they can lead to battery breakdown, and some of those batteries can actually explode, so you have to be very careful. Now that nickel cadmium, so that nickel cad, that cad part comes from the name of the cadmium metal in there. Cadmium is very toxic to the environment. So this is why nickel rechargeable batteries, especially the nickel cadmium, they want you to recycle them and return those to waste disposal centers, because we don't want that cadmium out in the environment, because it's very disruptive to the biological ecosystems, because it's not good for the environment. Now another type of battery is the nickel metal hydride batteries. And this is an improvement upon the nickel-cadmium. So it's more environmentally friendly than the nickel-cadmium. They also have a rechargeable long life and they're light. And so those are some of the advantages why we've shifted to more of the nickel metal hydride batteries. So instead of the cadmium at the anode is a metal alloy with dissolved hydrogen on it. So you have the metal with a hydride on it. So metal hydride combines with the hydroxide to make the reduced metal. So here the metal would be in a +1 oxidation state. Here it would be in a 0 oxidation state. And then there's the lithium ion battery. The electrolyte is concentrated potassium hydroxide. And the anode is graphite impregnated with lithium ions. And graphite, that's the same thing as your pencil lead. So it's sheets of carbon, and it kind of looks like chicken wire. And they stack on top of each other. And you've got intermolecular forces. And remember, intermolecular forces are very weak. So these sheets of graphite slide past each other. That's why the graphite is very slippery, and it's also used as a lubricant. And when you write, you're laying down sheets of the graphite. And in between the sheets of the graphite, you've got little pieces of lithium in there. So you've got lithium ions impregnated between those sheets there. At the cathode, you've got lithium and you've got a transition metal oxide. So here you have the lithium transition metal oxide. So you've got the lithium ions and the transition metal oxide here. And work on the lithium ion migration from anode to cathode, causing a corresponding migration of electrons from anode to cathode. So the electrons flow from anode to cathode. And these lithium ion batteries are rechargeable. They have a very long life. They're very light and they're more environmentally friendly, and they give a much better energy density than the previous nickel batteries. Now this brings us to fuel cells, and these are like batteries, but the only difference with the fuel cells is you have reactants that are constantly being added, so it never runs out. So where the previous we had the batteries, if we used up all the chemicals, the battery died, and you had to either recharge it or replace the reactants. In a fuel cells, you're constantly adding more and more reactants. Here we'll actually have an example of a hydrogen-oxygen fuel cell. And the anode and cathode both have platinum-coated metal. And the electrolyte is a hydroxide solution, so the hydroxide's in solution. And at the anode, you have hydrogen. So here is the hydrogen inlet. You're importing the hydrogen here, so that's H2. It combines with the hydroxides, and that makes water. So the hydrogen goes from a 0 oxidation state to a +1. So at the anode is oxidation, the hydrogen is oxidized. And at the cathode, here you're supplying oxygen gas. So at the cathode starts with a consonant, so reduction happens at the cathode. The oxygen gets reduced from 0 in the O2 to -2 in the hydroxide. And so from combining in the oxygen and the hydrogen, these two half reactions, we get the electrons being transferred in the circuit, and we get the electric circuit here. Let's go revisit some of our cells. Remember here, this was our voltaic cell, and we had zinc metal here at the anode, and the zinc 2+ ions in solution, and the copper 2+ over here, and the copper metal in solution. And when we hooked it up to a voltmeter, we could see that the potential difference between these two half cells was 1.1 volts. And this was a voltaic cell. The electrons flowed spontaneously in this direction from the zinc to the copper side. But in an electrolytic cell, we're using electrical energy to overcome the energy barrier and cause a non-spontaneous reaction. So this has to be a DC source, a direct current source. So we hook it up to a voltage source, and we're going to cause electrons to flow in the opposite direction. So we have to put in energy to make the electrons flow in the opposite direction that they would normally flowed in a voltaic cell. Now in the voltaic cell, so the spontaneous cell, the voltage difference between them was 1.10 volts. But for the electrolytic cell, you're going to have to put in a little bit more than the 1.10 volts to get it to go in the reverse direction. And that extra amount of voltage that you have to add to it is called the overvoltage. So in this electrolytic cell, we have a battery, and so at the negative terminal of the battery, the electrons flow from the battery and they flow to the cathode. And again, at the cathode is where reduction takes place. So at the cathode, reduction takes place because they both start with consonants. Here, the zinc 2 plus ions are being reduced to zinc metal. So the zinc 2 plus ions are picking up the electrons from the battery and depositing to make zinc metal onto the surface. And because we are losing zinc 2 plus ions in solution, the cation from the salt bridge is having to flow into the cell to replace the zinc 2 pluses that are being consumed. And then on the other side, at the anode, this is where oxidation occurs. So they both start with vowels. Oxidation is the loss of electrons. So the copper metal is losing electrons to make copper 2 plus, and it's giving up those 2 electrons, and those 2 electrons then flow to the positive terminal of the battery. So we're flowing in the opposite direction than what we saw in the voltaic cell, where in the voltaic cell we went from here to here. Electrolytic cell, the electrons flow from here to here. So as the reduction occurs over here at the cathode, the zinc ion metal piece here, since we're going in this direction to make zinc metal, the mass of this electrode is going to increase. So mass increases because we're making more of the zinc solid. But at the anode, because we're using the copper metal on the anode to make more copper 2 plus in solution, the mass of the anode is going to decrease. So let's take a look at that again on another cell. We're going to break this down again. So in an electrolytic cell, so remember, electrolytic cell differs from the voltaic cell in where we have to add energy in to make the electron go in the opposite direction. So in the electrolytic cell, the positive terminal of the battery attaches to the anode. So you've got the positive terminal attached to the anode because at the anode you have oxidation and the electrons are being produced. Those negatively charged electrons flow to the positive end because negative always goes to positive. And then the negative terminal of the battery attaches to the cathode. So the electrons flow from negative to positive. And so in this, the cations are attracted to the cathode. So the cations in the salt bridge are attracted to the cathode, and the anions are attracted to the anode. And those cations pick up electrons from the cathode and are reduced, and the anions release electrons to the anode and are oxidized. So again, at the anode where oxidation occurs, so they both start with vowels, the anions are attracted to it. So at the anode here, where we have the oxidation, and you're producing a lot of copper 2 plus ions, the anions in the salt bridge, so I'm just going to make up a salt, so salt, sodium plus and chloride minus, the anions are attracted to the anode to make up for all the 2 plus ions that are being added to solution. And the anode is connected to the positive end of the battery because this is producing electrons, and the electrons need to flow to the positive end. And because we are going from copper metal to copper 2 plus, we're losing some of the copper onto the electrode surface. This is going to lose weight in the electrolytic cell. So the mass of the anode is going to decrease. Now in the cathode, where reduction occurs, the cations are going to be attracted to the cathode. So the cations, like the sodium plus here, will be attracted to this side of the solution because we're losing the zinc 2 plus ions in solution. So we have to add more cations to balance out the charge so that we have equal charges on both sides. So this one gets connected to the negative end of the battery. And this one's going to gain weight in an electrolytic cell because we're making more of the zinc metal. And when we're doing electroplating, the electrode, which is the cathode, is where the plating takes place when we're doing electroplating. So we're adding more metal onto the surface of the electrode. So that gets us into the concept of electroplating. So if you have any chrome work done, or if you have a piece of jewelry and maybe they don't want a lot of gold on it or a lot of silver, they'll plate the surface of it. So you have a very thin layer of the metal that you desire on the surface of it. So in electroplating, the workpiece is the cathode. So here we have a ring here, and we want to deposit silver on the outside of it so it looks nice and pretty. So the cations are reduced at the cathode, and they plate the surface of the workpiece. So in this system, this electrolytic system, we have a silver electrode, and this is at the anode. The silver metal becomes silver ions, and those silver ions migrate over to the other side, and they cover the surface at the cathode here. So the silver plus goes to silver metal and covers the surface of this ring. So the anode is made of the plate metal, and the anode oxidizes and replaces the metal cations in solution. So since we're talking about electroplating, we're trying to figure out how much metal we need to put on the surface, how much metal we want to put on the surface, we can use Faraday's law. And the amount of metal deposited during electrolysis is directly proportional to the charge of the cation, the current, and the length of time the cell runs. So if we use the charge that flows through the cell, that's going to be equal to the current multiplied by the time. So it's this law that allows someone to calculate how long an electroplating process should occur at a particular current so that the right amount of metal can be deposited. Because you don't want to waste a lot of silver. Silver is very precious and very expensive. So why add more and more layers of silver to something if you don't need to? It's cheaper to put maybe a smaller layer on it. So you can calculate how much you actually need using Faraday's law. So here's an example problem. Calculate the mass of gold that can be plated in 25 minutes using 5.5 amps for the half reaction where gold 3 plus gets reduced to gold metal. So we know that the number of electrons that are transferred are 3 moles of electrons per every gold 3 plus. And they gave us the current as 5.5 amps, and the time is 25 minutes. They want us to find the mass of gold that's going to be electroplated during that time period. So using the time in the amps, we can get the charge. And then from the charge, we can get the moles of electrons. And from the moles of electrons, we can get the moles of gold. And from the moles of gold, we can use that to get the grams of gold. So using the time and the amps, we can convert to charge. And using the charge, we use Faraday's constant to get the number of electrons, and then using the balanced reaction of 3 electrons for every 1 mole of gold, we get the number of moles of gold, and then using the molar mass of gold, so grams per mole, we can get the number of grams of gold. So let's just see how to set that up. So if the time is 25 minutes, the amount of current that's passing, so it's 5.5 amps, so that's coulombs per second. So to get the coulombs per second, I need that second to cancel out with something, and this time is 25 minutes. I convert minutes to seconds, so 60 seconds are in 1 minute. And then using the amps, so 5.5 coulombs per second. And then using Faraday's constant, so the charge of 1 mole of electrons is 96,485, so coulombs cancel out. Seconds cancel out. I forgot to mark those out. Now I'm in units of moles of electrons, and then from the balanced reaction, for every 3 moles of electrons are needed for 1 mole of gold, so it's a 1 to 3 mole ratio, or I can say 3 moles of electrons for 1 mole of gold metal. And the molar mass of gold is 196.97 grams per mole. So when I multiply that out, let me just cancel out my moles of electrons and my moles of gold. That gives me my mass of gold. So after 25 minutes using a current of 5.5 amps, and for this reaction, we will plate 5.6 grams of gold onto the surface. So let's look at electrolysis. Electrolysis is the process of using electricity to break a compound apart. And this is done in an electrolytic cell. So you've got to put in some energy to break things down. And this can be used to separate elements from their compounds. And this is how we generate hydrogen from water for fuel cells. And this is also how we recover metals from their ores. So this is very important for our geology majors. So here we have an example of an electrolysis, and it's actually pretty cool. And you can do a similar setup at home, and I've seen it being done with a plastic cup and a couple of thumbtacks at the bottom and a couple of test tubes on the top to catch the gases. But at the anode, the water is going to be oxidized and you generate oxygen gas. And at the cathode, where reduction takes place, so the water gets reduced and you produce hydrogen gas. And hopefully you can tell, so if we're taking water, so I'm going to say 2 equivalents of water. When we break that down, that breaks down to 2 equivalents of hydrogen and 1 equivalent of oxygen. So there we have our balanced chemical equation. So here you can see that this is where the hydrogen is being generated because it has twice the volume of where the oxygen is being generated. So I think that's pretty cool. So we're doing electrolysis of the water, splitting the water up into hydrogen and oxygen. And we said that the oxygen was being generated at the anode. So here is our anode and here is our cathode. So that's where the hydrogen is being produced. Here we have the electrolysis of pure compounds. So this is where we're talking about purifying metals. So it must be in the molten or liquid state, and the electrodes are normally graphite. And the cations are reduced at the cathode to metal element, and the anions are oxidized at the anode to non-metal element. So here we have the electrolysis of sodium chloride. So we're actually creating sodium metal and chlorine gas. At the anode, the chloride ions from the sodium chloride, so this is molten sodium chloride, so melted salt. The chlorides are oxidized to make the chlorine gas and the 2 electrons that are given up. So those electrons then flow through the inert electrode, and so we get the chlorine gas generated at the anode, and it looks like there's a typo there that probably doesn't need to be there. And at the cathode, the sodium ions combine with the 2 electrons and it makes sodium metal. So this is actually how you get pieces of sodium metal. You actually have to do electrolysis because the sodium itself is very reactive and you're not going to find sodium metal in the environment. You're actually going to find it as its cation. Now when you have mixtures of ions, things get a little bit more complicated. So when more than one cation is present, the cation that is easiest to reduce will be reduced first at the cathode. So we're talking about the least negative or the most positive reduction potential. And when more than one anion is present, the anion that is easiest to oxidize will be oxidized first at the anode. So we're talking about the least negative or the most positive oxidation potential. So remember, the larger, more positive that value is, the more favorable the reaction is to occur. And the more favorable one always happens first. So let's look at electrolysis of aqueous solutions. And this is complicated by more than one possible oxidation and reduction. So at the cathode, you can reduce the cation to metal. So maybe you've got some kind of metal 2+, and you can reduce it to metal solid. You also have the reduction of water to hydrogen. That's a possible reaction. So here water is being reduced, so water gets reduced to hydrogen gas and 2 hydroxides. And the reduction potential of that reaction is minus 0.83 volts at standard conditions. But you have to remember, at standard conditions, we said that standard conditions was 1 atmosphere of gas, 25 degrees C, and 1 molar concentration. So 1 molar H plus is a pretty high concentration of protons in solutions. That's pretty acidic. But if we're talking about neutral conditions where the pH is 7, remember that the H plus concentration is 10 to the minus 7th. But this is at non-standard conditions. So I'm going to get rid of that because that tells me I'm not, since we're not at non-standard conditions, I can't have the knot there. So at the higher pH, so at a pH of 7, that voltage is more positive. And at the anode, there are 3 different possible reactions. You have the oxidation of the anion to the element. You have oxidation of water to oxygen. And at pH 7, that value for that oxidation is minus 0.82 volts. And then we have the oxidation of the electrode. So this is particularly a problem if you're using copper as an electrode. And this is why graphite is often used. So we saw graphite being used in a lot of those batteries. So the graphite doesn't oxidize, so sometimes that's used instead of other metals like copper. Half reactions that lead to the least negative E total will occur unless overvoltages change the conditions. So the least negative E total, so we're looking for the more positive value. So electrolysis, here we have electrolysis of sodium iodide with inert electrodes. So they're already telling me that I don't have to worry about the electrodes undergoing oxidation or reduction or anything like that. I'm not going to worry about that. Here with the sodium iodide, so we have sodium ions in solution and we have iodide ions in solution. So our possible oxidations are the I minus going to I2, or since we're in aqueous solution, maybe the water gets oxidized. And so there's the value of the oxidation of the water. And we're using the value at pH 7. So since this value is more positive, so it's the least negative number, so this is the largest number, this is the most favorable reaction. So the I minus is going to be oxidized before the water will be oxidized. Now let's see what happens with the reduction. So our possible reductions are sodium getting reduced to sodium metal, and the reduction potential for that is minus 2.71 volts. But for water, the water can also be reduced, and when the water gets reduced, that reduction potential is minus 0.41 volts. Well, this time the water has the more positive value, or the largest value. So the water is going to be reduced before the metal will be reduced. So the oxidation that occurs is the iodide reaction, and the reduction reaction that occurs is the reduction of water, if we're looking at the electrolysis of sodium iodide. So when I add those two equations together, the overall reaction is the 2I minus plus the 2 waters going to form I2, hydrogen gas, and 2 equivalents of the hydroxide ion. So I simply added these two equations, and notice that my electrons are canceling out. And if we want to know the E cell of the reaction, we add the minus 0.54 plus the negative 0.41. So that gives me, for the E cell, of minus 0.95 volts. So we're going to have to put in a little bit more than 0.95 volts for it to reverse that reaction to do the electrolysis of the sodium iodide. Okay, so let's talk about corrosion now. Corrosion is the spontaneous oxidation of a metal by chemicals in the environment. And since many materials we use are active metals, corrosion can be a very big problem. So an active metal would, for example, would be iron. And rust is simply the hydrated iron 3 oxide. And for rusting to happen, there must be moisture present. So there's got to be water present, and water is actually a reactant. And this is required for flow between the cathode and anode. Now, if you have salts around, so electrolytes, they promote rusting. So this is why you see a lot of rusting, especially out in the ocean and things like that, because you've got a lot of salt in the water. And those electrolytes enhance the rusting process because it's going to encourage current flow. And then acids also promote rusting. So the lower the pH, the lower the reduction potential is. So the lower the reduction potential is means it's going to be the greater oxidation potential. And the greater the oxidation potential, the more favorable the oxidation occurs, the rusting process. So So we're just going to look at rusting, and rusting is really a lot more complicated than just iron going to iron 3+. So what first happens at the anode, so the piece of iron metal itself, the iron acts as the anode, so the iron metal goes to iron 2+ and it gives up 2 electrons. So the iron metal gets released into the solution to make iron 2+, and those 2 electrons then flow to the cathode. And at the cathode, so oxygen from the air combines with water and the electrons that are produced from the anode, and it makes hydroxide ions. Those hydroxide ions that are produced at the cathode then combine with the iron 2+ ions that were created at the anode, and they form the complex iron 2 hydroxide. So that oxidation state of the iron there is a 2+. That's because this compound has an overall neutral charge, and each hydroxide is a -1. And since there's 2 of them, so 2 minus, the iron has to be a 2+. So once you create this iron 2 hydroxide species, so here we have that iron 2 hydroxide species right here. It combines with other oxygen from the environment and more water to make iron 3 hydroxide. So here the iron goes from iron 2+ to iron 3+. So the iron gets further oxidized in this reaction. So this is the final, so there you have the iron hydroxide happening. So rusting is really a kind of a complicated process, but you have to have water and you've got to have oxygen for it to react with the iron metal to make the iron rust. Because here we're looking at kind of the overall process where iron 2+ combines with the oxygen to make iron 3+. And in addition to this reaction taking place, you've got multi-step acid-base reactions, other equilibriums that affect the course of rust formation. So here we have the iron 2+ reacting with the water to making the iron hydroxide, then you get the protons. And then the iron 3+ can also do a similar type of reaction. And then you also have to have the dehydration equilibria. So here we have the iron 2 hydroxide, and that goes to make iron oxide and water. And the iron 3 hydroxide makes this iron oxygen OH compound with water. And then this compound then can form the iron oxide, so this iron 3 oxide, so this rust being formed here. So rusting is really a lot more complicated than you may initially have thought. Now, one of the ways that you can prevent corrosion is either to do something about it to prevent that corrosion from happening, or have something else that's less expensive to corrode instead. So one way to reduce or slow corrosion is to coat the metal surface to keep it from contacting corrosive chemicals in the environment. So maybe paint the metal to keep oxygen from reacting with it. Or some metals like aluminum form an oxide that strongly attaches to the metal surface, preventing the rest from corroding. So once you've got that oxide layer on the surface, it protects it from forming any more oxides and any more corrosion. But the problem with iron oxide, the rust, that's very brittle and often flakes off, and it kind of eventually you get a hole in something. Like if you have a truck sitting outside, eventually the rust will eat through and make a hole in the side of the metal. The other way of preventing corrosion, so either you've got to protect it from happening, or you can protect one metal by attaching it to a more reactive metal that is cheap. So you can create a sacrificial electrode. And galvanized nails are actually an example. So here we have an iron pipe, and so the iron pipe is made out of iron, and you don't want it to rust. So what they'll do is they'll attach this sacrificial electrode that's made out of zinc. And the zinc is more reactive than the iron. So rather than the iron getting oxidized, the zinc gets oxidized first, and that saves the iron pipe. So that's pretty cool the way that it works. Okay, so that ends our chapter on electrochemistry. If you have any questions, be sure to bring them to class so that we can get anything straightened out that you may not understand from these videos.